Today is the third session of the NADP CLAD Critical Loads of Atmospheric Deposition seminar series. Today's talks will be by Linda Pardo and Justin Coughlin, discussing critical loads of nitrogen and sulfur for decreased tree growth and survival. There we go. This is session 3 of a 7-part seminar series that we've set up through the NADP. The previous ones were an overview of critical loads and focus on epiphytic macrolichens. Next month, we're going to be talking about herbaceous species and herbaceous richness. So please, hope you can make it back on April 28th. I want to give a quick overview first of, I guess I should introduce myself for those who don't know. My name is Mike Bell. I'm an ecologist with the National Park Service Air Resources Division, kind of focusing on how air pollution is impacting national park resources and using critical loads to help guide policy and management decisions. One of the great organizations we work with is the National Atmospheric Deposition Program, which is based out of the Wisconsin State Lab of Hygiene in Madison, Wisconsin. For over 43 years, they've been monitoring deposition of air pollutants through 5 national networks set up across the US, with the National Trends Network currently having 263 sites. Within the NADP, there are 4 science committees focused on deposition, critical loads, aeroallergens, and mercury. And these use the data that we're collecting through this monitoring network to better understand how much air pollution is being deposited to the ground, as well as what happens when it gets there. If you're interested in joining NADP or learning more about it, there are listservs available to stay up to date with each committee, and you can find more at the website listed here. And just to note, the NADP spring meeting is going to be the week of May 10th, so if you want to dive in, really get to know what's going on, you're welcome to join us. CLAD particularly is one of these science committees. We facilitate technical information sharing around critical loads with a broad multi-agency and entity audience. The goal is really to fill gaps in critical load development, so understanding what the thresholds of air pollution are that cause change, and provide consistency in development in using those critical loads to guide management and decision making. Generally, we have large meetings twice a year. So at the upcoming spring meeting, we're meeting on the 10th, and then at the fall meeting in November, we'll also have focused interactions. Just like previously, I will put a link in for a post-seminar survey. Just we're looking for feedback, getting a sense of what from these presentations is really good and working for you versus what you would like to see more of, or how they could be more relevant for you working at an agency or your general interests. I would like to introduce our presenters today. First up is going to be Linda Pardo from the U.S. Forest Service. She's an environmental engineer in a research position with the U.S. Forest Service Northern Research Station and is based out of Burlington, Vermont, and at the Hubbard Brook Experimental Forest. Her research focuses on nitrogen biogeochemistry and temperate forest ecosystems. She began working on critical loads in the late 80s and has continued to lead and participate in efforts to coordinate and synthesize critical load work in the U.S. She currently serves on the CLAD Advisory Board and co-chairs the CLAD working groups on uncertainty and critical load synthesis. And then following her will be Justin Coughlin, is an environmental scientist with the U.S. EPA Region 5 in the air monitoring and analysis section. He is tasked with investigating hazardous air pollutants, leading monitoring campaigns, and conducting source apportionment analyses. He received his BS and MS in environmental science from the University of Pittsburgh, with a thesis focusing on reactive nitrogen deposition surrounding hydraulic fracturing well pads. He currently serves as the CLAD secretary and is assisting in the development of the NOx/SOx PM secondary standards in REA. So with that, Linda, I'll let you take it away.
Okay. Getting there, getting there. Okay. I think we're up there. All right, thanks, Mike, for inviting us to present our work on the tree critical loads. I'm going to talk about our current knowledge about air pollution effects on our forests, specifically how trees respond to nitrogen and sulfur deposition, and how we apply this information to setting critical loads for trees across the US. I'm going to focus my talk on nitrogen deposition, and Justin's going to focus on sulfur deposition, so you can kind of see the range of effects, but with hopefully fewer repeat figures and maps. Okay, so I'm gonna first show you some of the detrimental effects of nitrogen and sulfur deposition on trees, and then give you some background about the analysis that we did and the critical loads for nitrogen and sulfur deposition, and then show you an overview of the critical loads that protect tree growth and survival, and then talk about the range of critical loads that we observed at the species level, and finally take a look at what this looks like spatially across the country. And then Justin's going to go in more depth from there. So trees are susceptible both to sulfur and to nitrogen deposition, and their sensitivity varies by species, but also the types of damage that they exhibit varies. And we can see effects that are caused purely by acidification with sulfur deposition. With nitrogen, nitrogen acts as, it can contribute to acidification, but it also acts as a fertilizer. So it increases growth, which is, you know, often considered a positive thing when you're putting fertilizer in your garden. But too much nitrogen can disrupt the ecosystem cycling and lead to significant harm. And so these nitrogen types of effects are called either eutrophication or excess nutrient nitrogen. So the types of responses to end deposition that we see are shifts in biogeochemical cycling, alterations in tissue chemistry, changes in growth, mortality, or health, and shifts in community composition. I also just want to point out that although the deposition levels for both sulfurs, especially sulfur, and also for nitrogen in most regions, have declined considerably, the current levels still leave many areas at risk. And it's also something to think about that, especially for trees as long-lived organisms, that the legacy effects of prior acid deposition can still be impacting the trees in later years. Okay, so there, one of the responses that we see is elevated tissue nitrogen, which can lead to increased herbivory. This can lead to alterations in the composition of, or the structure, the composition of the system. For example, in this instance on oak species in Long Island with a pretty major leaf loss. For some tree species, and I'll talk about this quite a bit, we see declines in growth or survival with increasing end deposition. There are other sometimes multi-step impacts too, besides the growth and survival responses. So in the example on the left, you can see winter freezing injury of red spruce needles, which can lead to crown deterioration and tree mortality. So elevated nitrogen and sulfur deposition contributes to foliar calcium deficiencies that predispose trees to winter injury. On the right, you can see the results of nitrogen additions at Mount Ascutney in Vermont of 16 kilograms per hectare per year that increased the mortality and led to the canopy transparency you see in the upper panel. Okay, now I got to figure out how to turn on my pointer. Okay, here it goes. All right. So these types of secondary stressors are difficult to measure, but can result in catastrophic changes to the forest structure and composition. So I'm just going to show you one more, and this is from an ice storm that happened in 1998 in Vermont, and the paper birch trees that had been impacted by acid deposition, so that base cation, soil-based cations were depleted, essentially that meaning that the calcium that the trees needed to take up was no longer available in the soil. The paper birch on those poor soils that had been impacted by acid deposition were not able to recover from the ice storm damage. And ice storms are predicted to increase in the future in the Northeast. I put this in here to point out in part that there are a lot of different sequences or pathways for detrimental effects to occur. The analyses that Justin and I are going to be talking about tree growth and survival response patterns to deposition currently represent the best scientific information that we have on a broad scale and have the great advantage of being national in scope. However, they don't include all types of detrimental responses to the cascade of effects that can happen from elevated deposition levels. So the critical load is defined as the deposition below which there's no harmful ecological effect. So as the deposition increases, so we have deposition increasing along the x-axis, and the condition of the receptor goes up on the y-axis. So you get to some point where the condition begins to decline, and the deposition at this level is the critical load. So given the increasing information about detrimental effects of end deposition on terrestrial ecosystems and aquatic, it's become possible to set empirical critical loads for nutrient nitrogen and for acidification. So the critical loads are being used broadly at this point across federal agencies. They're used in to assess potential impacts of polluters. They're used in the forest planning process. They're used in the NEPA process, and they're used in collaborations, for example, here with the Rocky Mountain National Park, excuse me, and or local or regional organizations. And most significantly, they're used by the EPA in their review of the NOx/SOx impacts to determine whether a secondary standard for air pollution would be appropriate. So in 2011, we assembled the existing information on empirical critical loads for nitrogen, and we synthesized this data at the ecoregion scale. So this is a map of that level of information. But in order to address the needs of resource managers and policymakers now, we've refined the empirical critical loads in this analysis and other analyses like the lichens last month and the ones coming up that you'll see next month, by providing a finer scale individual species information, including sulfur deposition as well as nitrogen deposition. And another important piece is clearly documenting the uncertainty associated with the critical load. So we did this national scale analysis funded by the Powell Center and led by Kevin Horn with Quinn Thomas, Chris Clark, and I. And the findings that I'm presenting are based on this analysis. So the Horn analysis is based on the U.S. Forest Service FIA plots that were resurveyed between 2000 and 2016. There are almost 70,000 plots, over 1 million trees included in this assessment. And the structure of the FIA plots are based on a grid across the country. And it's the same grid that's used for the lichen analysis, for those of you who saw that last month. And basically, this data set is really as good as it gets for assessing forest responses to environmental gradients in the US. So in other words, what we're presenting is the current kind of state of the art. Okay, so in the analysis, we were able to generate curves, response curves to deposition by species, and the curves describe quantify how growth is correlated to nitrogen, or how survival is correlated to nitrogen. There's obviously similar curves for sulfur. And so you can see that they're different kind of shapes. There are increasing curves. There are curves that have a hump shape, and there are decreasing kinds of curves. If the response was flat, there was no response to N deposition, or I'm just going to talk about N now, but you can extrapolate to sulfur. So we weren't able to set a critical load. So you might hear the phrase horn species, and that refers to the species for which we were able to develop critical loads. Okay. So there were 94 species that were ultimately included in the analysis, and you can see here that the number of species present varies dramatically by ecoregion. So these are the level 3 ecoregions. And you can see that it's very low in the desert and plains, as you would expect. It's higher in the east than in the west, mostly driven by water, I presume. And it's highest in the southeast. Okay, so this is how many trees there are present in each region. And this is a breakdown at the level 1 ecoregion. So what I just showed you was level 3. So this is the coarsest level of the ecoregions that we have. And you can see that there's quite a range in the number of species present, but the eastern temperate forest has by far the most species present. So now we're showing how many species were we able to model in the analysis. So one of the criteria, there were a number of different filtering criteria, and one of them was that there had to be at least 2,000 individuals for a species to be included in the analysis, so that we were confident that we had a broad enough range and a big enough sample to see a pattern if it existed. And then now the black shows the species for which we were able to estimate the critical loads. From this, you can see that we don't actually have response curves for the majority of the trees in each ecoregion. However, if we look at it from a basal area perspective, you can see that we do have by far the vast majority of basal area considered. So we're missing the rare, the infrequent species, but overall, across the country, we're including 88% of the basal area. So it does cover quite a lot. Okay, so we looked at both growth and survival, and one question is whether the growth or the survival critical loads would be lower. So you'd kind of expect that if a tree is going to fail, the growth will slow and then it's going to die. So you would expect that the growth critical loads, or at least I would expect that the growth critical loads would be lower than the survival critical loads. So here we're looking at the growth and survival critical loads, the survival on the right, growth on the left, and this is the deposition is on the x-axis, and on the y-axis is the count of tree species that have a particular critical load. So you can see the distribution of the critical loads. And you'll notice that it's a pretty broad distribution, goes up to about 20. But most of the critical loads are in the range from 2 to 7. And for survival, that includes about 90% of the critical loads. And for growth, that includes about 2/3 of them. So looking at this, in spite of my prediction, it looks like the survival critical loads are lower than the growth critical loads. But this isn't on a within species basis. This is them taken together. So when we looked at the within species comparison, we thought that perhaps there weren't that many species. There are only 12 species for nitrogen where we had survival and growth critical loads for both of them. And when we look at them, we see that the growth critical loads, for the most part, are greater than the survival critical loads. For some species, they're lower, but for most of them, they're higher. And this was also true for the sulfur analysis. In fact, it was more strongly true. Okay. So another question is, how do the eutrophication critical loads or the nutrient nitrogen critical loads compare with the acidification responses? So here you would expect that the nitrogen inputs leads to sort of a mixed response. There's detrimental effects and there are positive effects. So when nitrogen deposition is low, in a situation, you might initially have a positive growth response, and then you reach a certain point and it will start being a negative response. So so we would expect with the sulfur inputs, which have only a detrimental response, that the critical loads should be lower for sulfur. So now when we look at the data, so now we have the sulfur critical loads on the bottom, and you can see that all of them are lower than 5 kilograms per hectare. So in this case, as we expected, they tend to be lower than the critical loads for nitrogen. Okay, so now I'm going to move on to looking at this critical loads patterns by species. So the nitrogen deposition is on the x-axis. The species names are on the y-axis, common names on the left, scientific names on the right. And the symbols, I don't know how well you can see them, but the growth are the downward pointing triangles and the survival are the upward pointing triangles. And they're paired, so they're pointing towards each other. So like here, for example, Engelmann spruce, that's a pair there. I know it's not perfect, but okay. There's a lot of data here. So, and here, we've also arranged them from lowest to highest just to make it a little bit easier to look at. And here you can see that there's a big range of the critical loads, but most of them are below 10. And there's a bunch of them are between 10 and 15, and there only are a handful that are greater than 15 kilograms per hectare per year. Okay, so now this might be a little bit easier to look at. I've added in the support interval in each direction. So the survival are now colored blue and the growth are colored green. And note that the interval is not always symmetrical. So in some cases, the error bars are large, and those cases would generally be driven either by there are not that many trees, there are not that many individuals of that tree, the gradient isn't big enough to really see a response, or the response is just is not that strong. So I just also want to highlight there's some that do not have any error bars associated with them. And I guess I'll say most of the error bars are fairly small, as you can see. There are a few exceptions, but there's some that don't have any error bars at all. And those are because those were decreasing trends. So that means across the whole deposition range, the growth response or the survival response decreased. So there was no point at which there wasn't a detrimental effect. So here we can't really set a critical load in the same way. We can only say that the critical load needs to be below this value, or the deposition, the critical load needs to be lower than this value. Okay. So I'm just going to blow this up so you can see it a little bit, and just to talk about some of the species that have the lowest critical loads. So most of the lowest critical loads are conifers. So Engelmann spruce, the eastern hemlock are species that have both survival and growth critical loads, yellow birch as well. In these cases, interestingly enough, for these ones with the very low critical loads, the survival critical load is actually higher than the growth critical load, but that's in contrast to most of the rest of what we saw. All right, so there are multiple ways to use these critical loads in assessing the impacts on a resource. One of them is the exceedance, which gives you an idea of what area is at risk. But because we have these response curves, we can also do more than just say that a species is at risk. When there is exceedance, we can say how much we expect growth to decline by. So I'm going to show you a series of figures to demonstrate how we show the impact on the various species. Okay, so here's the response curve for an example species, longleaf pine, and deposition is on the x-axis, and the growth is on the y-axis. Because the growth rates varied a lot, we normalized them by the maximum growth rate so that the top of the growth response would be 1, but in this case, the actual maximum growth rate is about 3.6 kilograms of carbon per hectare per year. Okay. So I just want to also point out that when we get to this, this point is the critical load here, and when you're above the critical load, the growth rate is declining. But just to be clear, the tree is still growing. It's just growing at a rate that is slower than what it was before the deposition increased over that level. Okay, so we can look at, we can identify the deposition, which is responsible for different levels of reduction in growth. So with a 1% reduction in growth, the deposition that would be 14.5. For a 2% reduction in growth, the deposition that would be 15.5 kilograms per hectare. For a 5%, it would be 17.8, and for a 10% or more decrease in growth, it would be 20 kilograms per hectare. So these are pretty high levels of deposition, but I just wanted to show it to you on a curve that'd be kind of easy to see. So if we want to consider what this means for the critical load, we can show the critical load as a range using the confidence interval around the maximum growth point on the curve, which is the critical load. So this range would be the area of the critical load. We can also, one of the strengths of this is that we can quantify the analysis, and so we can show, say, a manager what range of deposition would be associated with a 1% decrease in growth. So that would be shown here for a 2 to 5% decrease in growth here, 5 to 10% decrease in growth, and a greater than 10% decrease in growth. So when we put it all together, then we can see the different points at which we have these different growth rates. Okay, so I dragged you through all of this because to help you understand the format of the figures, which show the, which allows to look at the impacts on many species at once. So, okay, so here we have, this is for a decrease in growth with nitrogen deposition, the depositions on the x-axis, and again, species going up the y-axis. And this gray means that there's no decrease in growth at this point, which means that there could be an increase, which could be a larger increase or an insignificant increase in growth. So that's the part of the curve going up to the place where where growth begins declining. So here we're focusing more on the detrimental effects caused by nitrogen deposition, so the colored portions of the curve. And you can see that some species decline quite rapidly with deposition, for example, here, and other species decline much more slowly with increased deposition. But it's clearly a powerful tool to look at the information to assess the magnitude of the impact. So, oops. Okay, so for example, if you wanted to know a given deposition level, this is 5 kilograms per hectare, it would be possible to see how the different species would respond. So the most sensitive would have a decrease of greater than 10%, like this Engelmann spruce or red spruce. Or other species which would have a decline of 5 to 10% would be like eastern hemlock or balsam poplar, or a 2 to 5% decrease would be like yellow birch, for example, or balsam fir. So you could also look at a range of deposition. So let's say you're looking across a national park, and this range of deposition might indicate the range that exists in the park, and that would give you an idea then of the range of the detrimental responses for those species that would be present at that site. Okay, so I'm going to switch over and show you a couple maps, but before I do that, I just want to say that the maps that I'm going to show you consider the most protective critical load in a plot. So they're done plot-wise, so there are a bunch of different species in the plot, and the most protective critical load is the critical load, the lowest critical load there, and that's what drives the critical load for that whole plot. So when we look at the maps, we see we can see the spatial pattern, and you can see that the lowest critical load, so more red is lower, happen in the southeast, sprinkled with intermediate ones, and in the Pacific Northwest and West. There's some of the lowest ones scattered throughout the Northeast as well. That was the growth. If we look at survival, as we saw before, the survival critical loads tend to be lower, and we can also, with a different kind of a different spatial pattern. So here, this kind of central part of the east has the lowest survival critical loads. So we can also combine maps and show the minimum critical load in a plot. So whichever one is lower, survival or growth. And this might be useful for someone who was trying to, understand simply what would be the most protective deposition level. So we can also look at the fraction of trees that have the critical load exceeded. So this is for growth, for nitrogen, or the fraction of species. So this is like the number of stems, and this is the number of species. And so what you can see here, if you look at the southeast, for example, is that there's not a big fraction of species, but it's most of the trees. So that those areas where not that many species dominate the basal area or the what's on the ground there. And then if we look at the survival critical loads are lower, the exceedance is higher across the country. So we have a lot of exceedance in just about every region. And then finally, this is my last map, I believe, we can look at the fraction of the basal area and exceedance. And again, we see the pattern that with the lower survival critical loads, there's a greater fraction, a quite significant fraction of the basal area that's an exceedance of the critical load. Okay, so we saw that the tree critical loads tend to be less than 10 kilogram per hectare per year, about 2 to 7 for nitrogen, less than 5 for sulfur. There are more survival critical loads than growth critical loads that have been estimated, and contrary to what I was expecting, the survival critical loads tend to be lower than the growth critical loads. But we saw significant exceedance for all critical loads types across the country. And before I turn it over to Justin, I just want to do a little plug for something that we've been working on, which is a tool that will allow us, so we're generating, as you may have gathered from this analysis, a lot of information, a lot of maps, a lot of figures, a lot of tables, and we want to have a way for you to be able to access them easily. So we're working on this tool that will be a way of hopefully easily being able to choose what area you're interested in, which critical loads you want, which type of deposition, which species in the case of the trees, and then download and access all of those maps. So, okay, thanks.
Thanks so much. There are a questions in the chat. Someone getting a feedback. Might just be me. Well, Stephanie, you can unmute yourself. You had a couple questions throughout that you can just ask directly.
Okay, I will. And I'm even typing a question now. So I'll go ahead and I'll finish this. I'll just put it in and I'll just put in the question. Okay, so let's go back to the top. And for those of you that don't know me, I'm Stephanie Conley. I currently work with the Office of Sustainability and Climate as a field liaison. Historically, I was the forest soil scientist on the Monongahela National Forest, where we had unprecedented levels of acid deposition due to coal-fired power plants. And I know a lot of my colleagues here have been working with them a long time. So one of the things that I want to go all the way back to the beginning, Linda, when we talk about foliar chemistry, you know, we've always thought that we got good information. And are we still in a trend where we can recommend to people that you still get good information from foliar chemistry monitoring, and we should continue to do that? And then one interest that I had was like, yeah, we do the N portion of it, but what about the heavy metals? Because that seems to be often where we see some toxicity. So what's your state of the state on that?
I don't know if it's the state of the state, but I guess it sort of depends what you're looking for and what you're doing. Like, so for example, like the work that Paul Schauberg and his group have done looking at not just total foliar chemistry, but like looking at membrane associated foliar calcium as a, you know, really kind of getting into the physiology of the plant. So understanding that that's what disrupts the signaling that prevents the plant from responding appropriately to cold temperatures and leads to winter freezing injury. So those kinds of things are like a kind of much finer instrument than long-term foliar monitoring. I mean, I think that, yeah, I guess I can't really answer it generally in the context of this kind of analysis.
Sure.
Because that's sort of a finer scale than we can really really deal with. And I think as you're kind of alluding to, you get some information from foliar monitoring, but there are a lot of factors that cause foliar concentrations to vary that may not be the thing that you're really looking for. So, I mean, I guess, you know, I think like for tissue chemistry, I think in a lot of ways the lichens are a better tool because they are only getting inputs from the deposition, and that it's not complicated by soil uptake and all kinds of, you know, mycorrhizal association or all those other kinds of factors.
Okay, good to know. On that chart where you had all the tree species, I was looking for sugar maple. I thought I saw silver maple, but then in the Latin name I saw what I thought was sugar maple. Is that an error, or did I just miss that?
I don't know if I want to put it back up there in case it's an error, but
Well, I always in the East, we always look at sugar maple as one of our indicator species. It's before this one because sugar maple's not on that one.
yeah,
Or
sugar maple is not that responsive, it turns out.
Right.
Oops, wait.
A lot of the studies, though, look at sugar maple decline, particularly in the Central Apps, and that's why I always key in onto that. So there at the very top, you see it says silver maple, but I thought saccharum was sugar. I might be wrong.
No, because sugar is saccharum.
Oh, yeah.
Yeah. Okay.
Phew. All right. Yeah, that's me. That's called your soil scientist looking at your Latin names. There you go. Okay. Then my next question was, is there a difference in critical loads for, say, mature trees and saplings versus seedlings? And I ask this because, particularly for the East, when we do management and we're looking for stand recovery, meeting NIFMA, National Forest Management Act, post-disturbance, particularly with timber harvest, we're often looking at a seedling response, to ensure that stands are recovering. Can you talk a little bit about that and what the difference might be here and how this information can be utilized?
I think that's a really important issue, and I totally agree that seedling regeneration would be a really important thing to have a critical load for, in terms of, if you want to think about like what's really going to cause a shift in species composition. Yeah. But it's not something that FIA monitors. They have something that they call something that makes it sound like you would want to use it, but it's like the trees that move into a relatively large age class. So it's not really saplings either. So I don't think that in these analyses we have the ability to do that right now, but I agree with you, because there's no reason to assume. In fact, there's good reason not to assume that the responses of the seedlings might be different than those of the trees, and quite possibly more sensitive.
Okay, excellent. And then I defer to Karen. She has the next question.
Yeah, Karen, okay. You can unmute if you want.
Thank you. Yeah, I just had a question on, I'm trying to see about how long this takes for decline to happen. I guess it's just more of a comment too, like, is this just depending on so many factors that it's hard to really pinpoint how long it would take for a tree to die over a certain amount of time with a critical load exceedance, I guess. Is that even something known? Is it just site related, or just depends on how, because I would think that the critical load or the deposition would go up and down over time, just depending on industry and weather patterns, and just so I just thought if there's anything out there about that.
Yeah, I don't think that we really have that level of sophistication at this point, because this analysis, it's looking at one time interval, so you could like continue to do an analysis over time. But I think the other piece is other work that's looking at other environmental factors like ozone, or trying to relate the growth patterns to temperature and precipitation, or other measures. So then you would get closer to being able to understand, maybe not exactly what the trajectory would be. That's a pretty, I think, tall order, but at least to understand which factors are going to push it to decline faster. So I think that's where we are.
Okay.
At this point.
Thanks.
Thanks. And then Robert, I'll let you ask your question, and then Justin, you can start loading up your presentation. I want to make sure we give you enough time to get through everything. And then after Justin talks, we'll have more time for questions, and Linda can also answer some in the chat as well.
Thanks, Michael. Thanks, Linda. Linda, just your calcium example made me think about a potential issue and uncertainty. So the horn curves were calibrated using like the mean deposition values from 2000 onward. I forget the exact time frame. one issue that could potentially arise is that sulfate deposition decreased by like 80–90% since the 70s. So the spatial patterns of sulfate deposition, which were higher in the 80s and 90s, they're highly correlated with the spatial patterns of sulfate deposition in the 2000s, but they're like, I don't know, 50% lower. So when setting a critical load, is there any concern about, you have the relative shape of the curves is correct, but the actual critical load might be, based on the horn curves alone, might be set too low?
Too low, meaning that we're getting a legacy effect and we're calling it the current deposition?
Correct. This is just something I thought about when you brought up this indirect effect of calcium depletion. So this is the first time it's occurred to me. I just wonder if you've thought about that at all.
Yeah, I think it's kind of hard to separate out, partially because I think that not just the trees take a certain amount of time to respond, but also the soil conditions are going to take a certain amount of time to respond. So yeah, I guess I'm not really sure if we would. Yeah, I guess I need to think about whether I think ultimately we would need to worry about that. Chris Clark, I see you flashing. Does that mean you want to say something?
Yeah, sure. Yeah, no, I think I just wanted to clarify one point of what the curves are and are not. But I think it's still a good point. Like, Robert, they're not the long-term average sulfur deposition. They are the average sulfur deposition between the measurement periods. So they're not like a lot of the other critical loads that just like the Simkin critical loads that just look at the long-term average and so might be conflated too high or too low. So this is the average deposition experience between the two dates when that tree was measured. That said, the legacy effects of what you brought up are still valid and could still matter. But we haven't, I mean, as you know, it's super difficult to know what that lag interval should be. Should it be, 3 years, 10 years, 20 years? Statistically, we can add all of them in, but they're highly correlated with one another, and it's really difficult to parse out. So yeah, it's something that we are aware of and trying to figure out how to roll it in.
Thanks, Chris. Yeah, and that clarification was really helpful. That's a big source of the uncertainty eliminated there.
Yep.
All right, thanks y'all. Let's hand it over to Justin now so we can get into application and discussing more about sulfur.
Okay, thanks, Mike, and thanks, Linda, for teeing everything up. I just want to do a check real quick. Mike, can you let me know if you see the laser pointer?
Yes.
Okay.
Got your screen, your voice, and your pointer.
Sounds good. Okay, well, thanks again, Linda. Great job on kind of teeing all the application stuff up. So just quickly on the outline for my portion of the talk, as Linda alluded a little bit to, is the FIA plot program. So I'm going to talk about that briefly and then go through the data inputs, walk through a case study, and then go into some of the national spatio-temporal effects, and then maybe some of the uncertainty metrics as well as land manager considerations that people should think about when using this data like this. So quickly, the Forest Service runs the FIA program, which has been reporting tree characteristic information since 1999 nationally. As Linda mentioned, it's developed from a national plot design, and I have a figure on the next slide that kind of shows what that looks like. The map here on the right is the plots that were used in the Horn analysis, the Horn et al. Analysis. So Linda mentioned that, we call them the Horn species, so you'll hear me kind of mention them like that as well. So these were all the plots that were used to develop those response curves. The first phase in this is remote sensing, and what that allows for is stratification, so classifying those land attributes And then, secondarily, there's ground measurements that are taken in the FIA plots, that can be used. So the design, like I mentioned, there's remote sensing that, allows for stratification of the land. Once that's done, there is that phase 2, which is the ground sampling. So the plot here on the right kind of shows an example plot where there's various plots of, a macro plot, a subplot, and micro plots in which measurements are taken. The macro plots are an acre in size. And so 10 to 20% of these plots are sampled annually, and that does vary by state depending on resource availability. And I just want to mention there is a slight level of uncertainty in the plot information that's gathered, and this is mostly due to protect private property information, and that's called fuzzing and swapping. And really all you have to know is that some plots are swapped, in order to protect information, and then some, then they're moved a little bit as well. So they might not be exactly at the point of a lat long, but they might be moved. I think it used to be less than a kilometer, and I believe it's less than a half kilometer at this point. So Linda was kind of mentioning basal area. So there's an estimate of the cross-sectional area of trees that can be made within these plots using the ground measurements. So basal area is measured by, going up 4.5 feet above the ground and taking a diameter measurement. And then there's a scaling factor that's applied of trees per acre. So then you can get a, amount of trees in meters squared per hectare. So it gives you an estimate of, the amount of trees within a given area. So this is done on the plot level, but then it can be scaled nationally. And what this tells you is, the estimated area of a tree within a larger area. So moving along, so a number can be estimated for species. So, say you had balsam fir and you did all these measurements, you scaled it up, and then you have an estimate of the basal area of the trees within, or balsam fir within a given area. But you can also want to look at the spatial distribution. So a Forest Service publication by Wilson et al. In 2013 actually estimated the spatial distributions using a nearest neighbor approach. And so what these created were continuous surfaces of basal area for individual species. And there was QA/QC that was done on these estimates using a hexagonal binning approach. So you can imagine the number that I mentioned is summed within a bin, and then it was compared to this nearest neighbor approach. And there was pretty good agreement. There are some, sorry, I apologize. There are some considerations that you need to make. But most importantly, the localized scale actually has higher uncertainty. So you might be estimating that there is a certain amount of basal area for a tree within an area, but it may or may not be present due to some of the approaches, or that estimate may be slightly off. But essentially, you can aggregate these continuous surfaces to understand a total basal area. So using all species, what is the total basal area in meters squared per hectare, within a given area. So we're going to hop back here to the 94 species that Linda had mentioned, the horn species. So Linda said, there's limited species representation. It's about 29%, but there is high basal area representation nationally. So on average, it's 88% across the country. There are certain pockets in areas of the country where we may have a lower, proportion to the basal area. And like I mentioned, there are resolution considerations to take. I mentioned kind of this edge of range problems. So, in an upcoming CLAD report that's going to come out in the Bridger-Teton area, there was a comparison done of the species present within the plots compared to the species present in the continuous surfaces. And if I remember correctly, I think there was 8 species that showed up as being present within the continuous surfaces that were not present within the plots. And then there was also 2 species that showed up in the plots that were not present in the continuous surfaces. So there's just some kind of considerations that you need to make, regarding uncertainty and whether, those species are actually present or not. Thankfully, at least in that report, I believe, and here's a comparison of showing the basal area comparison there, but thankfully, in this case, most of those 10 species were relatively rare and kind of resided down here closer to the 0, mark. So we're getting towards the application. Wanted to walk you through, some of the input data. We have a couple more slides as it relates to input data. But first, just wanted to show the nitrogen and sulfur deposition that we, are going to be using as inputs to the response curves that Linda was talking about. So here we have the 2017 through 2019 average nitrogen and sulfur deposition. Note the different scales between the two. You can see that sulfur deposition is much lower than nitrogen deposition. And you can also see kind of this agricultural impact from reduced forms of nitrogen deposition out here in the Midwest. And mostly everything that I'll be talking about from this point forward is going to be using this 2017 through 2019 average deposition maps. And so the next piece of information that we need are the response curves themselves. So, we can now use these for individual species. What we do within this application is we actually use a slightly modified version of what was used in the Horn et al. Publication. And it's a relativized equation. So it allows us to remove other effects such as temperature, pressure, size, and competition terms so that we can really just hone in on just the nitrogen and sulfur deposition. There are some parameters that are individual to each species, and so those are also used within that response curve calculation. So we've walked through all the data that we need to make these types of assessments, and so we're going to hop into the case study at this point. So today I'm going to focus on Superior National Forest, which is roughly 2 million acres in size. So looking at the number of trees that were solely used in the Horn analysis, there were 22,000 trees present in Superior National Forest. And I'll mention that this is just the measured trees. So this obviously isn't the total number of these trees, but these are the ones that we have information for from the plots. So you can see the species present with their respective presence, that end value. And so some of the Forest Service's listed goals are here. Some of the goals in Superior are to ensure there's a greater tree species diversity, notably for conifers. Some of the deposition concerns include acidic deposition, which comes in not just from Minnesota, but also from other Midwestern states. And that nitrogen deposition, which can ultimately lead to nitrogen fertilization, can decrease species diversity. So that's something, of particular importance here. I do want to mention as I start moving forward, I'm going to solely focus on sulfur growth, whereas, Linda focused on nitrogen growth. I'm going to focus on sulfur growth, but we do have these for the 4 endpoints. So nitrogen, sulfur, growth, and survival rates. And I just want to show here in Superior National Forest the harvest rate. So if you're someone who's kind of interested in the harvest rates within a given area, you can see that over the last decade, harvest rates have stayed pretty consistent and have even ticked up a little bit in recent years here in Superior National Forest. So sticking with the case study area in Superior, we're going to hone in even a little bit further. We're going to talk about paper birch. Linda, I appreciate you throwing up a paper birch example in your talk. Teased this up pretty well. So, so we're looking at the sulfur growth rate response for paper birch, and so we're going to look at it within Superior National Forest. So first, here we're looking at the sulfur deposition between 2017 through 19, the average. And you can see here over on the response curve itself, kind of the range of deposition that we're talking about within the given area. Obviously, paper birch's sulfur growth rate response is monotonically decreasing, so we're going to expect a negative response here. You can see within Superior, the deposition ranges from about 1 kilogram to 2.3 kilograms of sulfur per hectare per year. And so now we're going to take that deposition and apply it to paper birch. So now what we have is actually the reduction in paper birch's sulfur growth rate due to sulfur deposition. So you can see, across the park, we range from anywhere from 1 to 12% reductions in the sulfur growth rate for paper birch. You can also see, I just want to make note here that the grid cell size of this example is actually at the 4-kilometer grid cell size of the deposition. You can see here, the little white areas, there's no species or there's no paper birch present within those areas. So you're going to kind of see those pockets show up. It's only where those continuous surfaces predicted that paper birch would be. Like kind of where we want to move to is we actually want to understand what's the basal area reduction that's occurring, not just the actual total reduction in the rate, but actually the basal area that's being reduced. So we can kind of rejigger this a little bit to get there. So now we've taken the basal area of paper birch to the total basal area. So it's proportion to the basal area. And so now we're looking at the reductions in total basal area for paper birch, related to its growth rate. So you can see kind of the difference between the two. I'll hop back real quick. So you can see kind of these large swaths, but then once you take it into the proportion to total basal area, you see lower reductions occurring in the sulfur growth rate. So, throughout here, anywhere ranging from 0 to 1% reductions in the total basal area, just for paper birch. But now what we can also do is we can aggregate it up a level. So now we're going to pull in all of the species that are present within Superior National Forest and look at what the reduction in the total basal area is for due to sulfur deposition and related to its growth rate. I apologize, it's a mouthful with all the different kind of variables you need to talk about. So you can see there's a larger reduction that's occurring in Superior National Forest once we pull in those other species. Again, ranging anywhere from kind of 0 to 4.5% reductions. But you can see as we pull in these other species, there is a wider impact or maybe larger impact than what we saw just for that paper birch example. So now we've done this for Superior, but we can scale it up nationally. So looking at it nationally, on the left, what we're seeing here is the reduction in total basal area as it relates to the sulfur growth rate for the entire country. So this is using all the species that are present in the horn species that are present nationally. We can even take it one step further and we can actually convert it to the basal area itself. One point to make here is, this is based on growth rate. So the amount that's being lost, that's being shown here on the right, is actually, the future growth that's being lost. It's not necessarily, lost immediately. So we can see, out in the West, we're losing, larger areas or larger amounts of basal area. A lot of that's due to the sensitivity of the species that reside out west. Like Linda alluded to as well, was the conifers that really tend to be pretty sensitive here. So we see large swaths in the west losing higher amounts of basal area. So everything we've been looking at has been kind of a spatial representation. We're going to kind of start moving into maybe some more of the temporal trends, but I just want to make one note here as we start to kind of move in that direction about what we're seeing nationally, over time as it relates to deposition. So on the left here, you have the sulfur deposition trends nationally. And then on the right, you have the nitrogen deposition trends nationally. So you can see these substantial reductions in the sulfur deposition over time across, all the various species. Interestingly, on the nitrogen deposition side, you can see, kind of a leveling off here a little bit around 08. A lot of what that is some of the reduced forms, NHX primarily, going up as some of these oxidized forms of nitrogen go down. These reductions have been largely due to the decrease in EGU emissions, among other things, as a result of stricter regulations and stricter air quality standards. So we've looked at everything spatially, but now we're going to look at it spatiotemporally. So we're going to pull in these, the 20 years of deposition that we can look at and how it relates to the various trees, nationally. So what this is showing are actually the 4 endpoints. So this is one example where I do have all 4 endpoints. So growth nitrogen, survival nitrogen rates, growth rates for sulfur, survival rates for sulfur. And what this shows is actually the worst impacts to a tree species via a 5th percentile. So imagine you have data for a tree species and you're taking the most detrimentally impacted trees from that species. That is what the 5th percentile would be. And so what these lines are lowest smooth lines with standard error that include all 94 species over the 20 years. So we're looking at the worst impacted trees out of a given species, and then we're looking at all of them together over time. And so that does have a spatial component too, right? You have to think about it because you're looking at the trees spatially, and then you're looking at it over time. So there is a spatiotemporal trend that we can kind of tease out. Some of the interesting stuff that comes out of this is you do see, and I should note, I apologize, that on the sulfur side, you're going to see all negative responses. On the nitrogen side, you may see some positive responses as well. You may see some, increased growth rates as, from nitrogen. So, I mentioned on the previous slide that we've seen the sulfur decreases in deposition over the last 20 years, and you can see that trend occurring on the responses as well. It makes sense, you're pulling in the sulfur deposition values, right? But there obviously is some, deeper details to that, but it's interesting to see how, positively responding the trees are over time with that decreasing sulfur deposition. Similarly, on the nitrogen side, you kind of see that leveling off that I talked about, around 08, 07. So, in some of the growth rates, it has leveled off on the nitrogen side as time has gone on. So I'm going to flip things on their head a little bit. Everything we've, let me hop back. I'm going to flip things on their head a little bit. I think one kind of direction we've started to take things as well is looking at what level of protection do we want to consider? Is 10% reductions in growth rate, is that too much? Typically we land around, and I won't speak for all of CLAD, but in this analysis, we're going to look at 5% growth rate reductions. So what do we want to do to prevent 5% growth rate reductions? And there's a lot of considerations to make on that front, but what we can actually come up with is a deposition value that would prevent 5% growth rate reductions. And so we're going to look at that for sulfur here. So imagine I've created a deposition surface. It's not going to be the next one, but I've created a deposition surface that tells you how much sulfur deposition is needed so that we don't go over that 5% mark. And so what we can do is use that surface, and we can take where we currently are with sulfur deposition, and we can subtract the two. So I've taken the 2017 through 2019 sulfur deposition average, and I've subtracted out, what we need to prevent that 5% reduction. You can see out here in the West that, it's between 0 to 1 kilograms of sulfur per hectare per year. That's primarily due to the fact that we can't really go down much further in the West as it relates to sulfur deposition. Over here in the East, another, what you can see is that there are some levels of reduction that could be had. in order to prevent this 5% growth rate reduction. And I will mention here that, when this analysis is done, we're looking at the most sensitive species. So we're looking at the minimum. And so we want to protect the most sensitive species. So, that should protect everything that's above it at that point then too. But these are really handy because, it shows us, how much further do we need to get to in order to prevent these levels of impacts. There are considerations that need to be made about what level of impact are you trying to prevent. So I'm going to move in now to some of the uncertainty metrics, and I think these will be particularly useful for folks who are using this type of data. There's a slew of uncertainty metrics that need to be considered, and you need to come up with a decision tree at how to get to that point. So briefly, I'll just kind of run through these. I'm not going to dive into them too much because they get pretty convoluted, but overall, the types of metrics that we can look at is we can look at the plot level data, as I mentioned earlier. We can look at the continuous surface data. There are various kind of spatial scales that one may be better than the other. When you get down to really fine spatial scales, you may want to consider using the plot level data as opposed to the continuous surface data. Makes for a prettier map with the continuous surface data, but it's just a consideration that needs to be made as to how much uncertainty you're willing to take on. Additionally, you also need to think about the nitrogen and sulfur correlation. So because we use a relativized equation in this analysis, you may have some collinearity of nitrogen and sulfur effects on a given tree species. And so you just need to consider, if there's a nitrogen and sulfur correlation and it's pretty high, are you really able to kind of parse out that nitrogen or that sulfur effect? A couple other ones, and I think Linda alluded to this too, is kind of the stability of that critical load. So in the model runs that were done, a best model was chosen, but sometimes there was an alternative model that may have been almost, good enough to use instead. So sometimes though, you can consider whether the other model was a better fit and how much the critical load changes by when you use that other model. So that's another consideration to make. The VIF, the variance inflation factor, is another kind of collinearity measure. And there's different kinds of thresholds. Typically we use 3, 5, and 10 that you'll want to consider when using this type of data set. So first off, we're going to kind of look at the comparison between the plot level data versus the continuous surfaces. So here on the left is the continuous surface, and then here on the right is actually the median of the plot level. So here I've taken a median across all the different tree species surfaces as it relates to their response for sulfur growth rates. And I've done the same on the right, but I've actually scaled it to a point layer, right? So you have, let's say you have 10 trees, you take the median of that within a given plot, and that's what that's showing there, here on the right. So spatially, visually, you can look at it, you can say, yeah, the trends look pretty close, spatially, you don't see too much of a difference. But then when you actually pull those together and you compare them, you can see there are certain differences that do occur. The blue line is the linear regression. There's a density here. Each one of these black dots is an individual plot level median compared to the continuous surface median. And so overall, the Wilson rasters actually underpredict a little bit compared to the plot level medians. But you can see there's kind of different trends that occur. This is pretty hot off the presses analysis. I can't speak to it in a whole lot of detail, but what I would expect is maybe some of these kinds of different trends that you see are likely due to some regional influence. If you have certain pockets of sulfur deposition that are occurring, and you would expect, something like this to occur. So, but that's one comparison we can do. It has a pretty good R squared and p-value. As I mentioned, the slope's 0.74. So, the Wilson is under predicted a little bit, at least in this analysis. So continuing to move on to the other uncertainty metrics that need to be considered, I spoke about the stability of the critical load, the VIF value, the NS correlation, and then this agreement coefficient. If you recall, for those hexagonal bins compared to the continuous surfaces, that's what this metric is what Wilson et al. Did within that paper. And you can see the various kind of scales that need to be considered. What this what this table shows is a species level removal. So in the last one, we were actually looking at how things looked at spatially at a plot level. These are all related to the species, so the 94 species. And so what you'll see here are the 4 different endpoints, so nitrogen and sulfur, growth and survival. And then you'll see remain or removed. If it remains, that means it meets the criteria. If it's removed, that means it does not meet the criteria, and it wouldn't be used in the analysis if you kind of, decided that you wanted no change in the critical load within your decision tree. So I just show this kind of as an overarching concept that, there are all of these different considerations that need to be made. You can look at it in a tabular format, and you can also look at it visually in a figure, right? So we're looking at the 3D plots here. You can see that AC value, you can see the VIF value, as well as the NS correlation. And what the color gradient actually shows is if there was a different model that fit, how much did that critical load change by in the different models? So, there's very few that change by a whole lot. There's one species up here that's roughly 2 kilograms of sulfur per hectare per year. But, the NS correlations and the VIF values tend to be the ones that remove the most species. You can see that in the table in the last one. You can kind of see it here a little bit. There's a fair amount of species that have a high NS correlation, so you can't tease apart that nitrogen and sulfur effect. So we can look at it at this species level. This is kind of an overarching concept, but then we can take it one step further, and we can actually look at what does that mean nationally. So when you filter out these species that maybe you have a higher uncertainty in, what does that look like when you do it spatially? And this is what it looks like. So for growth sulfur effects, we have taken a response using all the species, and then we've taken a response using only the filtered species. We've taken the difference of those two. So if it's red, it means that you see less negative impacts or more positive impacts. If it's blue, and I should say you see less negative impacts for when you filter it, right? So if you filter down from 94 to 60, let's say, you see less negative impacts when you're only looking at those filtered species as opposed to using all 94. If it's blue, it means that you actually see more negative impacts at the plot level. So this is the plot here on the right is the species that meet all 4 of the criteria here on the left. So you can see here we've only included species that have VIFs lower than 3, only species with NS correlations below 0.7, only species with stable critical loads, and another metric down here that I'm not going to get too far into. If it's black, you actually lose coverage. So it means that after you've done that filtering, those species aren't present anymore. There's no coverage at that point of any species. So, we use it this way as well, just to kind of show the range of what the impact might be, after you've removed some of these uncertain species. So I'm going to move here into the land manager considerations and then wrap up. So, when land managers are using this type of data, you need to make decision trees. You need to make these types of determinations about, the uncertainty metrics that you need to consider. What amount of uncertainty do you want to allow for? And these are going to vary on spatial scale, and ultimately they're going to vary based on your objectives as well. And I will do a little bit of a plug here. CLAD, particularly Working Group 2, is currently working on creating a ranking system for those various metrics. So the ranking system will actually allow for those types of decisions to be made without having to maybe get too far into the weeds on the details of everything. And we're almost out of time, and thankfully I am wrapping up. So, I'll take any questions now, and just wanted to throw some acknowledgements up. So, thanks.
Awesome. Thank you so much, Justin. That's it's kind of intense.
Yeah, it's a lot. Sorry.
If you have any questions, feel free to add them to the chat or raise your hand and we can call you out. So I guess I'll ask something. Oh, Stephanie, you can go.
Yeah, I want to go back, and this is a question for all of the folks that are behind this presentation, and I want to go back to, even at the end of Linda's awesome presentation, what we hear from decision makers and management and land managers is the air is getting cleaner, fossil fuels are on the decline. But what we're seeing from presentations like this, there are still impacts to forests, there's impacts to growth, which also implies that there's a potential impact to future ability to sequester carbon, which now we're focused on carbon policy instead of maybe clean air policy, which ironically the two go hand in hand. Does anybody have a statement about that or some advice about how we continue to stress the importance of decision makers and land managers to pay attention to atmospheric deposition?
Yeah, that's a pretty loaded question. Yeah, I don't know if other folks at EPA have thoughts. I think the approach we're taking at EPA is kind of laying it on the table as to the range of impacts. I think ultimately what we run into is that there needs to be decisions made about what level of impact we're trying to prevent, right? And I think that it all needs to kind of start at that point, and that isn't always the easiest thing, I guess, to kind of, nail down. So I'd open it up to other folks who have, are helping on this project, but that's kind of my 2 cents, I guess.
Justin, yeah, that was a great question. This is Robert Sabo, and I think Jason Lynch might be able to speak to it a little bit more. But in terms of atmospheric deposition, there's a lot of other factors at play in terms of like NOx concentrations, PM concentrations. So there's considerations of human health standards. Continuing to decrease NOx, SOx emissions to meet human health standards is still a priority. There's also unexpected potential co-benefits of cleaning up the air in terms of water quality. We're also exploring the implications as Linda has illustrated in terms of the impacts on other ecological services. So there's the human health standards, there's the secondary effects, and there's just emerging future benefits to cleaner air that's being revealed. So, but that's a great question. Yeah, in terms of striking the right balance and not losing sight the importance of if needed, further dropping NOx and SOx emissions. We have to make sure, that the research is at the forefront in terms of giving the information that the policymakers and decision makers need.
And I would just add to Robert, I mean, one thing I think, keeps coming up, in NADP, especially in the last decade, is, the increasing importance of reduced forms of nitrogen and, how that is impacted as we continue to decrease, the oxidized forms. Those reduced forms aren't getting scavenged for PM at that point. And so you actually have those reduced forms depositing. And I think, I know, in this research, we're going to kind of continue to go down the rabbit hole a little bit as it relates to those reduced forms and, what we can do for agricultural practices, among other things, to kind of start, ratcheting down that reduced form contribution.
And Trent, did you have a question or a comment?
Just two quick comments. I think number one would be is that one piece of the communication is this is recovery. So just because we drop below the critical load doesn't mean instantaneously everything's all better. We're going to be in this recovery phase. We've talked about that with some of the lichen work done in my part of the country here that doesn't reflect what the current deposition is. So there's a delayed recovery. What does that mean? And I think the other piece Justin talked about is the nitrogen story, especially in the Midwest. When you look at the NEDP data is kind of scary. So there's a different story to be talked about now. It's not sulfur, it's going to be nitrogen.
Yeah, I mean, the sulfur problem is mostly solved. I mean, a lot of the work that's been done in the last 10 to 15 years for those emissions, I wouldn't say it's solved, but there isn't much lower we can go in certain areas as it relates to sulfur. So no, I agree 100%, Trent.
All right, well, we're at 1:30, so I want to thank everyone for attending today. I thank you, Justin and Linda, for your presentations. Always learning so much, and good to see what the cutting edge version of this research is. I put a link in the chat to the survey, so if you have any comments on what you'd like to see in the future or what how you interpreted these presentations, we'd appreciate it. The next session is April 28th, and it will be on herbaceous critical load. So we hope to see you there.
Thank you, everyone. Appreciate it.